So we're up to now. Well, I'm kind of gonna skip 3.6 for now, but 3.7 hexagons.
Wait, do you have answers to this?
Huh?
I don't know.
Yeah. It might take me a while to explain it. It's quite long.
Yeah. Wait, I don't think.
Why is this
I can
so
tell you
short?
what the optimal answer is, but
What's the point?
it goes as 2k cubed.
Oh, it starts with 2k cubed. You did it wrong for long.
What do you mean by starting?
You can write it out as a polynomial.
What's the sequence?
Okay, so with hexagons, yeah? Maybe the first question should be like,
Oh wait, no.
if I write A, B, C, D, E,
Square root the expansion.
A, B, C, D, E, F is a hexagon, yeah? How many hexagons can I represent with the same 6 points? Okay.
6. Wait, no, 12. Wait, no.
18.
That's 12. Wait. Yeah, 12.
Yeah, I guess like there's 12 ways to label the same 6 points
Different 6.
to get the same convex hexagon, yeah?
Oh no. Not this again.
Okay, so there's 12. So you can start with any of them, right?
Yeah.
And then you can go in the clockwise to any of the either adjacent
then it'll
ones.
just be 6 factorial for...
Yeah.
What was the question?
What?
How many hexagons can you
Make with 6 letters.
Yeah.
How many hexagons
Yeah, like... If
Yeah.
you had 6 points, how many... It's hard to explain.
you can make?
Like, how many different hexagons can you make? Like, not like any hexagon.
Special.
Yeah.
Yes.
So I guess, yeah, like if you remember the quadrangles thing, right? You can have hexagons that don't go in the right order. You know? So like they
Why
could
did
go...
we skip pentagons?
Oh, well...
Because pentagons are irrelevant.
True.
It's a good
I mean,
question.
why settle for 5 and you can go for 6?
Why 7 or 6 when you could go to 7?
Why are we doing
I guess the question is, when did we skip pentagons, yeah?
Oh, okay. Then that's it to go, right?
hexagons?
So I think, okay, so the point of this chapter is that, like, I guess last time we already skipped pentagons.
Oh.
But the nice thing about hexagons is you can degenerate two of the points and you get a pentagon as well.
Can't you say that to like any polygon?
Yeah. Yeah, but I guess, I don't know, for some reason we have the 4 and the 6. There are pentagons in the next chapter though.
Wow.
Circle inside.
Why is it called Pappus rephrased?
Yeah, so I guess, yeah, so Pappus is when we already skipped, Pappus was already about hexagons, that's kind of what I was trying to say.
For each set of 3 alternate vertices of a hexagon is a set of 3 coordinate points.
Yeah, so if you have like a hexagon, right? Yeah. So that's a convex hexagon, yeah?
Yes.
It could be like this.
Ah, yes.
Yeah?
Hexagon.
It could be A, B, C, D, E, F, right? You see that? So that could be another hexagon, yeah? Okay. So we said there was 6 factorial sort of ways to start labeling the points, right? But like 12 of the labelings are the same, yeah?
12?
Because the labelings degenerate.
The lines would look the same.
Yeah.
Wait, no, that's
So there's only 60 ways. 60 ways. So it's 60 different hexagons you can get with 6 points.
What?
Okay.
How people are doing this?
That makes sense?
Yeah.
That makes sense. So there's 60 different hexagons you can get from the 6 points. Yeah.
60. 6 factorial.
Because there's 6 factorial ways to label it, right? So pick
Yeah.
A, B, and C and D, yeah, in order.
Yeah.
But then 12 of those ways are degenerate. So,
Just teach
They're
you.
the same.
because like if you start with B, C, D, E, F, A, it'd be the same, right?
Yeah, and you can go the other way.
And you can also go B, A, F, E, D, C. That'd be the same.
Yeah, and they're all the same.
Yeah.
Yeah.
And C, D, E, F, A, B.
So 2.
Yes.
Huh?
So for every time.
16, that's
So
more.
there's 6, right? And then there's times 2, so it's 12, yeah? That's 12. There's 60 different hexagons, okay? Does that make sense?
It's just.
So we have these vertices, yeah? So this is the convex, yeah? Okay? And then these are like sort of like the other 59, okay? And can you see that? So the way we call this, so if this is vertex 1, right?
Right.
So this is vertex A.
Oh.
Like this is vertex A, right? These vertices are called adjacent. Yeah?
Wait.
Yeah? Adjacent vertices to A.
Oh.
Yeah?
Yeah.
This is called the opposite vertex.
Mm-hmm.
Yeah? And these are called
Alternate.
alternate. Okay, so if you skip one, it's all adjacent. If you don't skip any, it's adjacent. If you skip one, it's alternate. Skip 2, it's opposite.
Mm-hmm.
Yeah? Okay. Huh?
He's still doing the
Nice.
other question.
See, can you see? So this is, I guess, what Pappus rephrase is, yeah?
Some
Because if you have this hexagon, right? Remember Pappus?
of the double. Yes.
Remember what Pappus was?
No.
Huh?
Wait,
So
what?
Pappus was this, right? If this was collinear,
Wait,
yeah?
we did this?
Huh?
Oh, wait, oh, the thing with the.
Yeah, so that's collinear, and that's collinear, right? Then this is collinear. Remember? That's Pappus.
Yeah.
Yeah? Yeah? So can you see that's how it works with a hexagon, right? So this is a hexagon, yeah? So it's saying if 3 alternate vertices of a hexagon, if each set of 3, so it's AC, yeah, it's alternating, ACE, yeah? It should probably, yeah. So ACE are alternating, yeah?
Yes.
This is skipping B and D, yeah? And B, D, F are alternating, yeah? So these 3 sets are collinear, right? Then the points of intersection of the 3 pairs of opposite sides. And the 3 pairs of opposite sides intersect, and the 3 points of intersection are collinear. Yeah? So 3 pairs of opposite sides would be, so let's look at the convex one to be more clear, yeah? B, C, D, E, F, yeah? So like ED, yeah? So ED is opposite to AB, yeah? Oh, oops. Okay. BC, is it opposite to
If it's
BC?
separated by 3 sides.
Is EC opposite to
What
BC?
does separated by 3 sides
No.
mean?
Huh?
What does separated by 3 sides mean?
Where? Where does that separate by 3 sides?
2 vertices of a hexagon are said to be adjacent.
I don't know.
Yeah, 2 vertices are said to be adjacent. Yeah?
Yeah.
That's what. I think that's what Michael got.
Huh?
He's still like both of us doing the other question.
Oh, yeah. Yeah.
Is
Oh,
that
it-
what my but
I think it is.
2k squared minus 1 plus
Wait,
k
what?
cubed
I
minus
thought it was this.
I had like 8k cubed on 3, right?
yeah minus 10k squared on 3. 8k cubed on 3 minus 10k squared
Oh,
on
you
3
expanded it out.
plus k.
Did you get 2k minus 1 on 3 before?
Yeah, I think that's what.
I got 2k squared minus 1 plus k cubed minus
Hmm.
10k squared on 3.
That's probably what he got. It's that, right? Yeah. I think.
And then this is the last part. Because that's the
Right.
that's this section.
That's important.
Well, that's this section.
You do it. Like,
So it's the triangular number and the minus 1. Because they're both there. So you didn't go to the end. Then go to the place where there's only one left. Right?
You know, I have no clue what you're talking about, but yeah. Yes, come on. I
That's
support
this
you
part.
in whatever you're doing.
That's just this part. Right? So 1 times 2.
Yeah, maybe I'll get the Pappus diagram.
4 times 5.
Yeah, it's just so random.
Until 2k. No, it's not. Times.
So the diagram we had
times
before.
1, 3,
No, it's
6,
not.
10. If you divide by 2, they're just triangle numbers.
Why you divide
C, E.
It's just 2 times the sum of triangular numbers. For all.
B,
I don't know how to write it. Oh, it's like
F, D.
Right. And yeah, it is. Just it. It's double the sum of triangle. Like, it's probably the same. You just did it in a different way. It doesn't really matter how you do it.
Remember that was Pappus' theorem, remember?
Yeah.
It was like those collinear and then this is collinear, yeah? Remember that?
Yes.
So that would be a hexagon, I guess. A, B, C. So this is hexagon, yeah? A, B, C, D, E, F, yeah?
Yes.
Okay. And then the opposite sides intersecting. So it'd be C, D, and A, F. Let's see. C, D, and A, F, they're opposite, yeah?
No, I just
C, D, A, F.
Yeah.
So A, F, C, D, yeah? That's the first point of intersection.
Oh,
And then it's C, D, then it's A, F, E, F. Wait, what am I doing?
what? No.
It's E, F, C, B, C, right?
Yeah.
E, F, B, C, yeah? That's here, yeah?
Yeah. And then E, D.
E, D, A, B.
Yeah.
E,
What's
E, D, A, B, yeah?
You can just do this.
Okay.
And then,
Does that make sense?
it's the same thing.
No.
Literally. Just getting smaller. The other one's going to be.
Okay. So it makes it, so can you see that that's Pappus rephrased into terms of hexagons?
Yeah.
Yeah? Because now you can think of this as a hexagon.
Oh, wait, I screwed that up. That's
Okay, and the reason they made these alternating points, yeah? So he makes a comment about the technicality of it. It's because huh?
It was the
This.
one with the 3, like with the 2 parallel lines, and like,
So
yeah, with the 2
You
lines,
prove that
and then like,
linear or something.
remember the one with lots of lines?
only those 3 EK.
yeah, so the reason they made them alternating points, okay, is because we had that technical condition at the start when we had a polygon. We can't have polygon with a collinear. So, like we can't have this collinear.
Mm-hmm.
So we can't have like
Oh,
FAB collinear in a polygon. So one way to avoid that, because you want these to be collinear, right, is to make them alternating. Does that make sense?
Yeah.
So you can't write A, B, C here, but you can write A, C, E here.
You should have solved those songs before coronavirus.
The game started after coronavirus.
Okay.
0 songs for Kavan.
Negative stumps, right?
Kavan's gonna
Alright, does that make sense?
blow all his money.
So there's yeah, there's like 2 exercises to try in that. It's a very short thing. Okay.
What if Corona?
Oh, I feel like we don't have time to do this.